Next, we have an innovation talk presented by Stephen Indyk, Director of Space Systems at Honeybee Robotics.
Let's see. Good afternoon, everybody. My name is Stephen Indyk. I'm with Honeybee Robotics. We're a small company that was acquired by a much larger company a few years ago. You may have heard of them, Blue Origin. My tenure at Honeybee has been over 12 years working in a variety of things that Honeybee does. We do a lot of sample handling in space, but I'll talk a little more about that in just a couple slides here. So a quick background of Honeybee for those of you who may not have heard of us. We have a pretty good reputation of developing systems for sample handling and sample acquisition in space in very rigorous environments, from places like the Moon or Mars or even Saturn's moon Titan. Honeybee has been around since the 80s, and one of the things we really pride ourselves on is we're a really creative group of engineers. We've developed a lot of different technology, a lot of testing, a lot of sample handling, again, abilities for these extreme environments that not only impact space, but also have relevance back here on Earth. I'll start off this talk generally with a few of our capabilities that we've had a lot of success with in space in the past year. Talk a little bit more about how demanding it's been to develop these technologies. And then I'll talk a little more about how AI might be able to help some of these technologies that we're developing for future missions and future applications as well. Honeybee itself is divided into two groups, one outside of Denver, Colorado, and the other outside of Los Angeles. Together we work pretty well together in developing a lot of these mechanisms that, again, are used for space. The images up there you can see on the slide right there, you can see some of our earliest successes in space. One of my favorite missions, Mars exploration rovers, Spirit and Opportunity, where we provided the RAT, the rock abrasion tool, to open up the rocks on the Mars surface. This is a pretty important capability because it allowed the scientists that were interested in Mars geology and Mars formation to see the unoxidized, the unweathered surfaces of these rocks and get much better science readings from that. So one thing I'm personally very passionate about, one thing I really love about Honeybee and what we do, is we work a lot with scientists to develop their payloads and their systems for space applications. Generally, I like to say I help make these scientists' dreams come true. A lot of very smart people, a lot of really big dreams, a lot of big ideas. And again, with AI, I think that we can enhance a lot of these capabilities and increase the turnaround time for them quite a bit. This is just a high-level list of some of the things that we're really good at Honeybee, good with at Honeybee. We, as our name implies, we do a lot of robotics work. We do a lot of mobility systems. We do a lot of avionics. But I think one of our real strong suits is kind of getting dirty with these things. Again, we do a lot of sample handling, sample acquisition. What that requires is setting up these involved environments, these vacuum chambers, these thermal conditions that are really rigorous, and then solving the challenges related to them. Again, if we're talking about sample handling, how do you pick up a rock on Mars? How do you move through regolith on the lunar surface? These are some of the challenges that we look at every single day. We do a lot of research, we do a lot of development. This slide captures our flight work that we're currently working towards. The dates are all relative. They're kind of out of date on this slide, so don't hold me to any of the years mentioned there. But this is just a nice track to say that we have a lot of experience in low Earth orbit with mechanisms and systems there. We have a lot of experience that we're applying to the lunar surface. I'll talk more about that in just a minute. We have a lot of heritage on Mars and the Martian surface. One mission I'm very excited about is the JAXA-led MMX mission, which will actually be the first sample return mission from the Mars planetary system. And we're providing that sample handling system that's going to grab that material and help bring that back. In addition to that, one other mission that I'm really super excited about is the NASA Dragonfly mission, which is a nuclear-powered octocopter going to Saturn's moon Titan. I bet nobody can say that 3 times fast. I know I can't. But it's a really cool, impressive mission that's going to bring back some of the finest information back from the moon Titan we've ever been able to have access to. And I'm very proud to be part of that team working towards that. The next few things I'm going to talk about are some of our recent successes in space and some of the technology that it's taken to develop to make these things successful. First one I'll talk about is our lunar planet vac system. Usually when you think of space, the environment you think of is this really harsh vacuum environment, absence of everything. One thing you usually don't think about is pneumatics or gas in space. The first thing you think of is just poof, goes everywhere, dissipates, disappears. Some of our really creative engineers and scientists on our side said, why do we not think about that? How can we utilize that capability, that really high delta pressure, that really high energy? How can we use that in applications that we might not have thought of before? And in this case, I'll talk about two examples of using pneumatics in space, specifically on the lunar surface. Again, you have that really hard vacuum, so maybe you can use that to your advantage. Maybe you can use that to collect the material on the surface. Maybe you can use that to port it over into a spot that you care about, as opposed to have a heavier, larger system, something like a robotic arm instead. So our system that we call Lunar Planet Vac, think of it like a vacuum cleaner, exactly the same sort of system that you'd have at home, except instead of just pulling up the material in an atmosphere, you're using that pneumatics, you're adding that gas to liberate that material from the surface and funnel it down a path of least resistance into a sample collection chamber. That's what our Lunar Planet Vac system does. Here you can see a cross-section of the cone that's used for Lunar Planet Vac with a couple of pneumatic nozzles in it that funnel that material up through that path of least resistance into a sample collection chamber. This is a system that we've had in development for about a decade at this point. We've worked with NASA, we've worked with other smaller companies to do a lot of testing, a lot of analysis. We were fortunate enough to be selected as one of the payloads on the NASA CLPS program, Commercial Lunar Payload Services program. So here in the next slide, you can see some of the testing we did. You can see one of the Maston landers out in the Mojave Desert, where we replaced the foot pad with one of the sample handling cones for the Planet Vac system. This was kind of creative at the time. You're now using that foot pad as a dual service. It's not only landing on the surface, it's also your collection system. More efficient. Again, a very creative idea. Here you can see us integrating our Planet Vac system on the Firefly Blue Ghost lander. It's kind of hard to see, but it's kind of in the center there, that little white cone with that big red safety cover on it. Take note of that, because in the next video I show you, that will be on the lunar surface. That one right there in that image. It'll be collecting sample. So I'll show you this video. I'll try to do it twice if I can. But we're going to see that cone drop down to the surface in just a second, and then it's going to fire the pneumatics, releasing the gas, collecting that sample through that cone. So here we got the lights on. There we're just firing pneumatics. We're in the vacuum of space. Oh, there goes Dwight, the Rock, Johnson, flying overhead there. Oh, and here you can see our team celebrating. Very exciting. This is years of work going into this to make that happen. I'll try to play that again one more time just so everybody can see the pneumatics in space operating. Let's see. Again, this is on the lunar surface. Drop the cone, release the pneumatics, liberate all that surface material. Some of it gets funneled down, path of least resistance through that tube into our sample collection area. Oop, hi Dwight. There we go. And then our celebration. Yay, everybody likes that. So what were the end results here? So these are images taken inside the sample collection bin of our container. You can see from left to right, nice, clean, no material in there. That's a good sign. The second one, after we fired the pneumatics, you can see how dirty and dusty it is inside there. We collected lunar regolith. That's great. That's a great achievement. And then finally, what you can't see in this image is there's a sieve right in the center, so it filters out the large from the fine particles of that sampling routine. So this basically proves that we can not only collect the material, we can also successfully sieve it into the size particle range that we might care about if we were to take the sample, pass it to a certain scientist's instrument. Very cool. The second one I'll talk about is our Lister probe, which also flew to the moon on the same lander, on the Firefly lander. This is a type of drill. Again, not just the drill that you find at Home Depot, something if you were drilling into concrete or something else that was difficult, hard. Those are usually rotary percussive drills. They have percussion like a jackhammer, and they have a rotary like a normal drill to kind of cut in and exhume the cuttings. This is a gas drill. Specifically, it's a coil tube drill. Smaller, lighter weight. Similar to Planet Vac, where you don't necessarily need something big and like a robotic arm to move in position to collect your material. This is a system that you don't need a big jackhammer-like drill to bore down below the lunar surface to collect a sample, or in this case, place a sensor suite. So here, in the lower left, you can see a series of images from one of our vacuum chamber tests. Again, test as you fly, mimic the environment. In this case, we're replicating the lunar environment. And you can see a lot of that regolith kind of showering around. You'll see that again in just a moment in the next video I show you. But the novel part here is we're not taking a big clunky drill. We're taking a coiled piece of tube. We're uncoiling it into a linear piece, similar to a straw. And then just like a straw, we're adding pneumatics through it. We're blowing into that straw, but in this case, we're in the regolith environment, which is very loose, sand-ish material that's then kicked up into the vacuum space. Again, high pressure, low vacuum in the environment, a lot of energy being excited. Here's a picture of our hardware on the lander. One orientation, you can see it's on the table, upside down. And the other orientation, you can see it's on the bottom of the lander. And with this video, again, you'll see we're looking down at the lunar surface. You'll see our probe start to bore down. You'll see a lot of material getting kicked up. So here you can see us test firing some of the pneumatics, slowly lowering, and you can see a lot of debris getting kicked up as we're slowly boring a hole into the regolith. Again, regolith is kind of like a loose material. It's kind of compact in place, though, and the pneumatic release is what's kicking it up, excavating the hole with relatively low force for a lot less mass than what a similar rotary percussive system might require. Again, you can see our team celebrating. I really hope that AI never replaces the idea of our celebrations and enjoyment that we can get from these big successes. With that, I'll talk a little more about what we're looking forward to in the future and where AI is coming into our realm, what we're doing for developing space missions, for developing instruments, for developing science hardware, etc. One thing that I'm very excited for in the AI realm is this idea of making our work, using AI as a tool, making our work easier, making our work more time efficient. Let our engineers spend more time doing what they're able to do, what they're really good at, which is being creative problem solvers for challenges that are very difficult, that are very challenging in space. You may have heard Blue Origin is planning on landing on the moon. They have a really nice lander to do this. One thing that we're working towards is developing a map of the lunar surface for when we get there. So we know where the safe zones, where the not so safe zones, where we might want to deploy science instruments, rovers, etc. And this image right here you see on the right, that's what we know is on the moon from the images that we have from orbit. Those are the best quality images that we have. That looks kind of blocky, kind of dark, kind of unknown. From all the science data that we have, all the rock distribution, all the particle size distribution, we know that it should look something like this. That's a lot of debris, that's a lot of material on the surface. These two images were developed using AI. This is using a video game engine. We're inputting a lot of the data about the particle distribution, what we expect to see on the surface, the rock size, etc. We're mirroring that, we're merging that with the known information from missions like LRO, Lunar Reconnaissance Orbiter, and other missions that have high-resolution imagery of the lunar surface. So this is not a true moon image. This is an image that's generated using AI to show what we expect the surface to look like. From this, we can do a lot more modeling, we can do a lot more analysis. We can pick out areas that we presume we should be able to land on, areas that have lower hazards. But these are some of the tools that we're using right now utilizing AI. Here's a video using that realm that we've developed. Again, it's one of the video game engines. And AI is factoring in all the lighting angles, all the surface topography, etc. So this is just a quick graphic of how we're doing that and how that can play out. But from this, you can manage a lot of permutations and a lot of iterations on what you might care about. Lighting conditions are very important on the lunar surface, in space in general. Thermal conditions are very important. You can model all these things in this realm. One of the missions that I'm also very excited about, which Honeybee is a big part of, is another Firefly landed mission, part of the CLIPS program. CP-21, Honeybee is venturing into making lunar rovers, autonomous lunar rovers in this case. And you can see one of the graphical representations of our rover for that there. It's a pretty standard lunar rover for what you would think is roving around on the moon, or will rove around on the moon. 4 wheels, suspension system, cameras, comm, solar panels, etc. Nothing too outlandish, simple, low cost. That's one of the main things about anything CLIPS related. But with it, what can we do to optimize the science that we're getting out of the lunar surface? And that's kind of where AI comes in. Operations is pretty tricky. A good day in operations is a very, very boring day. You don't want a lot of excitement when you're driving around the moon. That's exciting enough. Don't hit any rocks. Don't do anything too crazy. No wheelies, right? So keep it simple. In this case, we're applying AI for modeling what we can do with navigation, for modeling what we can do with sensors, etc. Here is a video using that AI realm, the modeling that we have for the lunar surface. And you'll see 3 different camera views of that. One is top down from the left of the image, and one moves kind of slow because that's kind of the holistic approach. And then the 2 other views are following the rover as it's driving, and then right in the front of the rover as it's driving. Both of those terrain navigations are AI generated. We created this realm. We said, hey, here are craters, here's rocks. AI, go from point A to point B. Do it safely. This is the course that it chose on its own. This is the path that it's deciding. And this is some of the tools that we're using to try to implement AI in our future developments for the CP-21 rover. It's pretty impressive. As was talked about earlier by Dr. Chen from JPL, there's been a lot of auto navigation that JPL has forefronted that they've done with the Mars rovers. And this is in the direct lineage of that. Instead of rover planners making certain coordinate selections or boxing out this area as far as we could drive, here we're just saying, here's the world. Go from point A to point B. Don't get stuck. Don't do damage. Don't be too adventurous, let's say. Another big part of all these autonomous driving kind of problems is it really is a data problem. It's a lot of data. You have sensors, you have cameras, you collect all this data. How do you process it? How do you turn it around in a really quick timeline? And that's one of the things that AI is really excellent for and really excels at. So the final project I'll talk about on the Honeybee side is one that I'm also very excited about. I think this is one of those AI-generated images. I know I'm not that artistic, so it didn't come from me, I promise you that. It's also very cute. But the idea here is thermal energy and regolith exchanger, or T-Rex. Nope, he's drinking his nice cup of warm tea. I like it, it's kind of fun. But the concept here goes back to one of the really big challenges for the lunar surface and the lunar environment itself. We have about 2 weeks, 2 Earth time weeks of daylight, and we have about 2 weeks of Earth time night on the lunar surface. That goes from a very hot temperature to a very cold temperature. Survive the night, that's the term. How do you survive the lunar night? You park your instrument, you park your rover, your lander, whatever it is. If you can't survive the night, if everything freezes, your electronics break, you can't operate the next day. That's a pretty big problem. And here you're going to see a couple images of the lunar diurnal cycle itself. But how do you survive the night? And this is just one of the solution sets that we're talking about, that we're working on using AI to solve that problem. There's been other concepts put forth before: thermal batteries, hot rocks, heat up things, park your rover on top of it, solar concentrators, concentrate solar energy onto a certain spot or to a certain system, keep that warm, and basically just let that cool off during the lunar night and reap the benefits of that dissipation from the thermal energy. Other solutions are bring a lot of batteries, right? Like if you really have to turn on heaters for a long time, bring a lot of batteries. Let that deplete as night goes on and generate heat from that. Space heater style thing. You can also bring radioisotopes to the surface, but that's kind of tricky because that's very expensive. There's a lot of other legal problems currently for getting radioisotopes and also getting to the surface, and then lunar surface. And then also what happens during the day, it's still very hot, you still have to dissipate that energy as well. Phase change materials are another thermal solution here, but that's also kind of heavy again. You get the kind of sense that I keep talking about mass, heavy, expensive. These are some of the biggest problems for surviving the lunar night. So our solution is not a mass or a volume-focused solution. What we were able to do with the solution set is convert it from mass and volume to a surface area solution. So how do we do that? This is a rough schematic of what we're working with. Instead of bringing all your material with you, why can't you live off the land? Lunar Institute Resource Utilization. Take the regolith that is plentiful, contain that regolith, put it in a big container, seal that container, bring up some gas with you. Use a heat exchanger to heat up that regolith during the day. Once it's heated up during the day and you transition into night, siphon off that energy. Well, this sounds like a lot of those hot rock things that you just mentioned. Similar, but it's very different in its implementation. Instead of just taking that hot rock and sitting on it, or staying in front of it like you're warming up against a fire, here we're pumping gas through that granular hot rock. We're cooling off that rock with the gas and transferring it through a heat loop to where we care about, to where we want it to be warm during the night. Let that gaseous rock mixture cool off during the night, transfer that heat, keep your habitat, your whatever system it is, warm during that period. That's the key here. I'll show you the next slide, which is basically that cycle that I just described. Starting at fill, where you collect that material, you put it in the chamber, you seal it off, you close off that chamber, to then during the day, where you energize that heat exchanger, you collect all the heat there, you transfer that heat to that regolith material, and then during the night, you live off the heat from that radiating material. Again, you're pumping gas through it. So you're kind of getting this weird mixture of regolith in this chamber that's full of gas and kind of this bubbling, almost separating loose regolith material. This is a pretty cool idea that one of our creative engineers came up with. If anybody knows anything about computational fluid dynamics, which I know is very, very complicated, and then you start throwing in all the thermal problems into it, I start looking at that and say to myself, there's a lot of equations that exist in that realm. There's a lot of math there. I'm not a big math person, but I know computers are really good at math. Can't we implement AI to take those really known equations, take the values that we know from the lunar environment, plug them into those equations, and then run a design iteration, a design problem, a design loop here to tell us how big that container should be, or how much energy we have to put into that container, or how much material we need in that container, or what about the shape of that container, the shape, the curvature, what are the optimal configurations for that heat exchanger? What about the siphoning of that gas? Where does it got to go? How do we do that? I wish I could talk more about that today, but stay tuned, because in the next few days or weeks, Honeybee will be talking more about the results from this AI-generated design problem. I wish I could talk more about it. It's really cool, but you just have to kind of bear with me on that one. But I can kind of end on that little bit of a teaser and kind of say, like, AI really is making differences in design engineering. I think humans are really creative problem solvers. Let the AI do the heavy lifting. Let it do the things that we know are solvable, the math, the big equations, all that sort of stuff. We've got a lot of great data there, a lot of great information there. Why don't we be the ones to tell the AI how to make our work simpler, easier, quicker, more productive? I'll wrap up on that. Thank you all so very much.